Running complex LLM inference across decentralized, vastly unequal hardware environments requires a massive departure from traditional networking models. Our cluster begins with a local legacy rig, an Intel i5-6500 with 16 gigabytes of RAM, connected to the network through an NROC tunnel. The second node is a cloud-based AWS EC2 M7 iFlex.large instance, providing a high-performance compute environment. Processing identical AI workloads across consumer hardware and premium cloud compute creates a significant performance gap. This asymmetry makes standard load balancing paradigms ineffective for real-time inference. A common industry approach is the stateless round-robin load balancer, which distributes incoming API becomes congested. This creates a significant disparity in user experience. Half of the requests face high time-to-first token latencies, while the other half process instantly. Fixed routing models completely fail to account for the harsh physical constraints inherent in these wildly heterogeneous nodes. Efficient distribution requires the network to be aware of real-time hardware telemetry. To achieve this, we look into the software architecture of the individual inference nodes. Both AWS and local nodes run an identical stack, Fast API serving as the interface for llama.cpp, loading a Gemma model. We configure parallel processing flags to enable 4 simultaneous requests per node, allowing the hardware to manage multiple inference streams at once. Fast API utilizes Python's asynchronous library to ensure non-blocking I/O, allowing the server to manage network traffic while the LLM engine performs heavy computation. Each node also hosts a dedicated telemetry endpoint. This endpoint reports CPU utilization, available RAM capacity, and active requests in the queue. By broadcasting these constraints, the nodes provide data necessary for intelligent routing decisions. A central orchestrator gateway in AWS now sits between the public users and the inference cluster. When a new request hits the completions endpoint, the orchestrator simultaneously pulls the status data from both nodes. This data feeds a node health score equation. Available RAM is weighted at 40%. Inference needs significant memory. Free CPU carries an equal 40% weight, dictating generation speed. Finally, active requests act as a 20% penalty, preventing node overload. However, identical CPU utilization does not always indicate identical performance across different hardware generations. To resolve this, we introduce an architectural bias variable. We add a static 20% base preference to the AWS node's score, reflecting its superior single-core performance compared to the older i5 processor. The routing logic combines dynamic hardware constraints with a static acknowledgement of the cluster's compute hierarchy. After identifying the target node, the orchestrator must route the user's payload. We use the HTTPX library for asynchronous proxying, minimizing the latency added by the orchestrator itself. In this decentralized setup, the NROC tunnel is a potential point of failure. If the local connection fails, the orchestrator must respond. We establish a latency threshold for the telemetry pool. If a node fails to respond within this window, it is flagged by the orchestrator. This triggers the failover protocol, which temporarily overrides the health score logic. The orchestrator routes 100% of the traffic to the AWS node, maintaining service availability despite the local hardware failure. This architecture provides both load optimization during normal operations and a safeguard against local network instability. We can monitor these interactions through a custom dashboard. It provides a real-time view of the side-by-side CPU and RAM usage alongside the request traffic distribution. This dashboard visualizes the asynchronous routing decisions made by the Python backend. The interface includes a load tester module to evaluate the orchestrator's performance under stress. Triggering 10 simultaneous requests demonstrates how the system handles a sudden burst of traffic. The AWS node receives the majority of the requests initially, as the 20% bias gives it a higher starting health score. As the AWS load increases, its health score drops, and the local node begins to accept overflow requests it can reliably process. The traffic graph confirms the mathematical model. The orchestrator dynamically balances the load to maximize the utility of the available hardware. Stateless routing models are insufficient for these types of mismatched, decentralized clusters. Telemetry-aware routing ensures that every node in a heterogeneous system is utilized according to its current physical capacity. System intelligence resides not just in the LLM's weights, but in the orchestrator that manages the underlying infrastructure.